So I'm going to do some applications of 14.7 and some Lagrange multipliers. What they're called, this is 14.8. So I'm going to erase this and come back with a problem. All right, so this is a classic problem where you have an equation and a function and a constraint to it. So it says find three positive numbers. I'm going to call those x, y, and z. The sum is 12. So these are all greater than 0. The sum is 12. And the sum of whose squares is the smallest possible. So I'm going to call S the sum of the squares, x squared plus y squared. This is 12 plus z squared. So I need to find the minimum of the sum. The min of the sum. S. This is the goal. Find the minimum of the sum. So this is in 4 space, this is a paraboloid, but in 4 space. This goes on up forever. But there's a constraint to it. And the constraint is that the x plus the y plus the z has to equal 12. So we'll call this the constraint. And this is just a regular generating function. So in 3 space, what this would look like, this is a plane, right? This is a plane in 4 space. In 3 space, what it would look like is the following. You'd have your bowl, and then you would have a plane cut it. And this plane would cut it. I'm going to make it really thin. And it would cut it in like a ellipse. And so the idea is to find the minimum of that ellipse. You find the minimum of this. All right. So there's a couple of ways there you can do this. There's 2 ways to do this. One is the direct way, directly. And then the other one is using Lagrange, what are called Lagrange multipliers. All right, this is 14.8. 14.8. So directly is to solve for a variable in the first equation and plug it into the second. Because I want you to find the minimum of s, but all my formulas and stuff are in terms of 3 space, not 4 space. So I need to get rid of one of these variables. So I'm going to solve for z in the top one. 12 minus x minus y, and I'm going to plug that into s. So s would be x squared plus y squared plus, and then 12 minus x minus y, quantity squared. I'm not going to square that out. So find s of x, would be 2x, and then the derivative of that last part is 2 times 12 minus x minus y. Derivative of the inside is -1, so that's -2. So s of x is 2x minus 24 minus 2x plus 2x, sorry, plus 2y. And then we'll set that to 0. So now we do s of y. So s of y is symmetric. So s of y will be 2y minus 24. Oh wait, I can simplify this. This is 4x minus plus 2y minus 24. So s of y will be symmetric, so it'll be 4y plus 2x minus 24. You set that to 0. All right, so I can take a 2 out of both. So 0 equals 2x plus y minus 12. And it looks like y is 12 minus 2x here. So if y is 12 minus 2x there, when you take a 2 out first, 2y plus x minus 12 equals 0. I'm going to plug in y equals 12 minus 2x. I get plus x minus 12 equals 0. So I get 24 minus 4x plus x minus 12 equals 0. So I get 24 minus 12 is 12. -3x plus 12 equals 0. So 3x equals 12. X is 4. So when x is 4, I'll go back over here and I get 12 minus 8 equals y. So y is 4. So we get 4 comma 4. And then when you plug that into the original S, okay, so if x and y are both 4, then z is also 4, because z is 12 minus x minus y. These are 4. This is 4. This is minus 8, so that's 4. So 444 is a possible max or min. So now what you would do is you would find your d, and we need f sub xx. So f sub s sub xx, s sub xx, so s sub x. All right. This is s sub x here. Oops. Yeah, let me leave the numbers in. S sub x is 4. S sub y, here's s sub y right here. That's also 4. And then s sub xy, I'll go up here, that's a 2. So 2. So out of all this, d would be 4 times 4 minus 2 squared, which would be 16 minus 4 is 12. It's greater than 0, so I know that regardless, 444 is going to be a local max or min. Once again, if we had found if any of these had an x or a y in them, you would just plug in 4 for x and 4 for y. All right, but we didn't get that, so we have that. All right, so now we find f sub xx, so s sub xx, and we plug in 4 comma 4. Well, it's already 4. It's 4, which is greater than 0, so that means there's a local min there. So apparently 444 is our answer, because that will give us the minimum of the sum. The squares of, so the sum of the squares is as small as possible, so that'll give the minimum. Add all those up. So let's try that out. So apparently 3 numbers that add up to 12, and the sum of their squares is a minimum. So this is a minimum. We need to make them all 4. X is y is z is 4. So there we go. So the reason why we can't just, well, we have to work in 4 dimensions. You have to solve for z and the, there we go. Let's play around with this for a second. Suppose I made x is 3, y is 5, and z is 4. So the sum of the squares would be, this would be 9, this would be 25, and this would be 16. So that's 34, this is 50. The sum of the squares, if they're all 4, would be 16 plus 16 plus 16 is 48. And that's smaller than 50. So that's just an informal check. All right, now, there's another way to do this problem, and that's using Lagrange multipliers, this one here. So the way you do that is you take your constraint and you give it a name. Call that C. C for constraint. C of x, y, z. And that's going to be x plus y plus z. And now you have S of x, y, z is x squared plus y squared plus z squared. I'm going to show you the method first, and then I'll show you why it works in a minute. So if you take the gradient of C, that's equal to a constant multiple of the gradient of S. So the gradient of C is C sub x, C sub y, C sub z, and then that's lambda times S would be S sub x, S sub y, S sub z, like that. So all the C's give you 1, 1, 1, 1. That's equal to lambda 2x, 2y, and 2z. So 2. So now you set these equal. So I get 1 equals lambda times 2x. I get 1 equals lambda times 2y, and I get 1 equals lambda times 2z. I'd solve these along with the constraint, which is x plus y plus z is 12. This up here. So pull this down. So I also have x plus y plus z equals 12. So if I solve for x everywhere and y, I'm sorry, x, y, and z, I get x is 1 over 2 lambda, y is 1 over 2 lambda, and z is 1 over 2 lambda, and that equals 12. So if I multiply by 2 lambda on both sides, I get 3 equals 24 lambda. So it looks like lambda is 1 over 8. So now if lambda is 1 over 8, that means that x is 4. So I get 1 equals 1 over 8 times 2 times x. That's 1/4, so this means x is 4. And if I do the same thing for y and z, I get y equals 4 and z equals 4. And this is much easier to work with. All right, so then another problem is what's called the aquarium problem. So I'm gonna pull that over, and I'll show you how easy it is to do with Lagrange multiple. Oh, let me show you the theory behind this first. What you have here is you have two functions. You have two functions. Both of them live in 4 dimensions. Constraint function, you have a generating function, your regular function. All right. Where they intersect, where their level curves intersect, the gradients are parallel. So, for example, if you have a bunch of level curves, let me pull a graph over from another page. Hang on one second. So what we have here is we have a function f of x equals x squared plus 2y squared. That is the function in blue here. No, it's the one in purple. So this is a paraboloid. This is one, it's in purple. So this is the paraboloid, and its level curves, it looks like this. Its level curves are in purple here. Now, then there's a disk. The disk is in blue. So that's this one here. So the extreme values of the paraboloid on the disk would be the following. So what I'm going to do is I'm going to draw both. You have your paraboloid, and then you have a disk below it. And that disk, like the paraboloid they've drawn in purple. So let's do that. Paraboloid. And then the disk is in like a light blue. So let's draw a disk below that. This. All right. So if you project the disk up to the paraboloid, then the disk is going to hit the paraboloid where the paraboloid level curves are parallel. Where they touch, the gradients are parallel. So the gradient, remember, to function is perpendicular to its level curves. So if you look, the two gradients are parallel. The gradient of the blue and the gradient of the purple, they're parallel wherever they meet. And that's where we're meeting. That's what we're looking at, where these things meet. So essentially, the level curves are perpendicular to the gradients of a function. The level curves of a function f of x, y are perpendicular to the gradients of f of x, y. All right. So the next thing is the maxima and minima of a function f subject to a constraint. A constraint C occur where the gradient of f is equal to lambda times the gradient of c. All right, so with that said, I want to do the aquarium problem. So let me go grab it and I'll pull it over. So if you need to, take a minute to read this, and I'm going to go ahead and draw the aquarium. This is wrong. And so here we go. So we have an aquarium. The base is slate, though. So the base is slate, the sides are glass. So I'm going to call this X, Y, and Z. All right, so there's a Z here and a Z here. Y's back there. All right, so the volume is X, Y, Z for sure. All right, the sides are X, Y, and it looks like there's Y, Z, and it looks like there's X, Z. Those are the sides. These are glass. So the glass ones are, these two are glass. And then the XY one is slate. If you look at the problem, this says it's slate. So slate costs 5 times as much as glass, it says. It says per unit area. So the cost of the glass is going to be YZ plus YZ, there's 2 of them, plus XZ plus XZ, there's 2 of those, it's the front and the back. The YZ and the YZ are on sides. And then the bottom costs 5 times as much. And these areas are, well, it just costs 5 times as much. So that'll be 5 times XY. So the constraint is going to be 2YZ plus 2XZ plus 5XY. So the constraint on the aquarium is that, and the aquarium volume is this. The volume V is constant. So what we need to do, no, the constraint, I'm sorry, the constraint is V. Let me use a different letter for this is the cost. I'll see its cost. I can still use it. The constraint is V because we need to find the minimum of the cost of the materials. So the goal is to find the minimum of this. Find min of C, the minimum of the cost, subject to V equals XYZ. So there's 2 ways to solve this. 2 ways. One is directly, and the second one is using Lagrange multipliers. Lagrange multipliers. All right. Directly is pretty long, because what you have to do, so we use these 2 formulas together, you would have to find the minimum of C. So the minimum of C is, if you notice, it's using 3 variables on the right. And our formula using f sub xx and f sub yy, all that stuff, they only use 2 variables. So I need to get rid of one of these variables. And to do that, I would solve for z here and plug it in there. So directly is pretty long because I would solve for z. So z is the volume over xy. And I would plug it into c. So c would be 2y, there's 2x times z, so it would be 2y plus 2x times z, which is v over xy, plus 5xy. And now I would do the whole cx equals 0, I would do the cy equals 0, all that cxx, cyy, all that, find D, and I'd keep going. But if you use Lagrange multipliers, all you need to do is set the gradient of V equal to lambda times the gradient of C, and you'll get your answer pretty quickly. So the gradient of V is V sub x, which is yz, V sub y, which is xz, and V sub z, which is xy. That's equal to lambda. Lambda is just a constant, just a Greek constant. Gradient of C, if you look at it, let's pull it down. Gradient of C is, all right, x would be 2z, y would be, x would be 2z plus 5y. Y would be 2z plus 5x. And then z would be 2y plus 2x, like that. And now you just set these equal. So I got yz equals lambda times 2z plus 5y. I get xz equals lambda times 2z plus 5x. And I get xy equals lambda times 2y plus 2x. There we go. And so if you look, in this case, so we're going to try to solve for, the goal is to solve for x, y, z, and sometimes lambda is needed too, just depends. And you can use your formula v equals xyz to help you out if you need to. The v is a constant. They give this to us. For this problem, it's a constant. So we can use that to help out. But what I notice here is the following. If you multiply the top one by x, this one by y, and this one by z, then all of these are equal. So if I multiply the top one by x, I get xyz equals lambda times 2xz plus 5xy. And then if I multiply the second one by y, I get xyz equals lambda times, this is z, 2yz plus 5xy. And then if I multiply the bottom by z, I get xyz equals lambda times 2yz plus 2xz. All right, so we're here. These are all the same on the left, so that means that these on the right are equal. So when we solve those simultaneously, when I set the first two equal, I get the lambdas drop out, I get 2xz plus 5xy equals 2yz plus 5xy. 5xy's cancel, and I get 2xz equals 2yz. The 2's can cancel, the z's can cancel, because z's not 0. It's the side of an aquarium, so x equals y. Hey, look at that. So now when I set the second two equal, I get 2yz plus 5xy equals 2yz plus 2xz. The 2yz's cancel out. X can't be 0, so I get 5y equals 2z. Right? X can't be 0. So apparently z is 5y over 2. So x is y, z is 5y over 2. And now I'm going to set the outer two equal. So this one, I'm going to set that one equal to that one. And let's see what happens. So we get 2xz plus 5xy equals, and remember the lambdas drop out, 2yz plus 2xz. And looks like this cancels with this. X equals y. X equals y, I got that from here. So when x equals y, I get 5 y squared equals, and z equals 5y over 2. That's from here. So 2y times 5y over 2. 2's cancel, 5's cancel, y squared equals y squared. Cool. So everything's happening correctly. So what I get then, I'm done. So this works out. This works out great. It's supposed to do that. So I get x equals y, and these are, and then I get z equals 5/2y. All right. So now I know that xyz equals v. So v is xyz. So I'm going to put this all in terms of y. So v is going to be y times z is 5/2 y. So this would be 5/2 y cubed. So this means that y cubed is equal to 2/5 v. So this means that y is the cube root of 2/5 v. All right. And so that also means that x is that. And then therefore z would have to be 5/2 times y. So it's 5/2 times the cube root of 2/5 times v. And you can play around with this and work it out, but this is good enough. And that's what the dimensions of the query have to be. So probably on a test, I would say, for example, I would say, let v be 25, or let's say 125. And so this would all be coming out nice. X equals y. Let me do this in a darker color. X equals y equals the cube root of 125/5 would be 2 times 25, which would be, well, I would have to work it out. I'd have to make it 625. 625. So now this would be 125. So this would be 5 cube root of 2, and then z would be 125 inside. That would be 5 coming out of that. So it'd be 25/2 cube root of 2v. Oh, this is a v here. Oh, no, v was 625. So there, cube root of 2. And there, you would have that. All right. And there you go. There's the aquarium problem.